So if we want to find the square of the A matrix, the way we do that is we first diagonalize it and we find the square of the matrix in the eigenvector basis. And since the matrix in the eigenvector basis is a diagonal, all we've got to do is take the power of the diagonal elements. And I worked that out in detail. Here, I just multiply this matrix by this matrix, and I find that I get this, which is then the square of this diagonal element, the square of this diagonal element on the same, in the same positions, and then the zeros in the same positions. So we just get a new diagonal matrix, which should be, and I did it right over here, but it's 3 squared, I know perfectly well, is 9. Okay? So then, this is the square of the matrix in the eigenvector basis. How do we get the square of the matrix down here? Well, we just use the usual diagram. Here we have our matrix with respect to the eigenvector basis. 4, 0, 0, 9, the matrix we just found here by squaring the diagonalized matrix. So now we want the matrix that corresponds to A squared. That means we start here, we use the inverse of the column of eigenvectors matrix. We apply our transformation, diagonal matrix, and then we use the column of eigenvectors matrix to transform ourselves back here. And here is the calculations. Okay? Furthermore, we could find, say, the 5th power of the matrix in the same way. Okay, be identical, it's just that this being the square of this, we would use the 5th power. So I wrote out, hey, I didn't calculate it, it'd be easy to calculate. Well, I calculated it down here. Okay, you calculate the 5th power of the diagonal matrix, which is just be negative 2 to the 5th, negative 32, 3 to the 5th is 243. And we multiply by the same transformation matrices, because the transformation between the standard and the eigenvector basis is what it is. It's always going to be the same here if we're going from the eigenvector, the diagonalized eigenvector basis, the diagonalized matrix representing the transformation in the with respect to the eigenvector basis to this. So whenever we're doing this picture, this is what we're going to do. We do this and we can calculate the 5th power of the A matrix. Okay, now we could calculate the square of this matrix, just multiply the matrix by itself. It's only a 2 by 2 matrix, that wouldn't be too difficult. Okay, we could calculate the 5th power. That would take a little more multiplication. The most efficient way to do that, incidentally, if we already have the square, is we square the square, giving us the 4th power, and then we multiply that by the A matrix to get the 5th power. But at that point, when you get 5th powers and up, it's usually much easier to do the transformation this way. Since you don't have to change this matrix and this matrix, the only matrix that changes with power is this one. You get into a relatively simple calculation scheme. Okay, of course, matrix multiplication is not completely simple, but you do get that. There's a lot more that you get by diagonalizing matrices, but within the scope of this course, we're just going to get to diagonalization, do powers of matrices, and a couple of other simple things, and leave the rest for more advanced courses. Okay, well, that's pretty much it for the Math 177 course, actually, which kind of ends now with the process of diagonalization. The 285 course continues on, and one thing the 285 course continues into, well, we go back a couple of chapters and we start putting magnitudes and distances and what we call norms and inner products on our vector spaces. And we start making sense of things and learn a whole lot more about matrices and transformations in the structure of vector spaces when we can put it's effectively putting distances, a measure of distance within the vector space. So we're going to do that next. 177 people are more than welcome to hang around, follow on with this. But this is kind of the last thing we do in the 177 course.